Hey, Mr. Keller, doing test corrections for exam 8. Alright, so number 2. Fulcrum is placed under the 20 centimeter mark of meter stick to balance meter stick. 75 gram mass hangs from 8 centimeter mark of meter stick. What is the mass of the meter stick? Okay, so as you see number 2 here, so you do the net torque, which equals 0, then equals mg, but it's 75 grams, so 75g, parentheses 12, because that's the radius from 20 to 8, because that's where it says it's the mass is placed, minus mg30, and you're looking for this m right here. And so you can cancel the g's because then they cancel by themselves. And then when you do all this math out, you get m equals 30, which is E, none of the above. Okay, then for number 3. In the diagram above, the bar is free to rotate around its center. Which force applies the greatest torque? Okay, so I made the mistake on the test of using sine 30. So then I would just say 2f, because then 2f times L is 2FL, which is more than f times 2/3 L, because that's just 2/3 FL. But if you use cosine 30, it actually equals like 0.86 repeating, or 0.86. So then if you do L times F cosine 30, you actually get 2.6 FL. So the answer is that the 3F on this is the greatest. That's A. Okay, now we move on to number 6, and you're supposed to use kinematics. And so you have delta theta equals omega initial plus t, or times t, plus 1/2 alpha t squared. And so then alpha initial, or omega initial, is 0, so that cancels with t also. So then it ends up as just 1/2 alpha t squared. So then the number of rotations would be delta theta, which is the radians, over 2 pi radians over radians per revolution. And so then when you plug in what it actually is, you get alpha t squared over 4 pi revolutions, which is E. Okay, and then we're moving on to number 8. Okay, so number 8, the rotational inertia around the 3m mass is blank, and the rotational inertia around the m mass is 7 ml. So as you see here, for this one, you're looking at this. Okay, so what you do is you do I equals ml squared plus another ml squared. And so for the first one, you get I equals m 2l squared plus 2m 3l squared, which is 22. So on the test, I thought, since I got 22, the second one must be 16. So I just circled B, but actually for the second one, you do 2ml squared plus 3m 2l squared, which is 8ml squared. So that's E, none of the above again. Okay, and then we move on to number 11. Okay, so number 11, the first part, you're looking for the tension in the cord. And so you have to do RF sine theta of all of the cord plus the center of the bar plus the force of the box. And so I thought the radius of the plank was 0, just because, but it actually goes from the middle, which is 1.4 meters. So then you do 2.2 F sine 90 for the cord, because you don't actually know the force, so you're looking for this force, and then plus 1.4, because that's the radius of the plank, times 14, because the mass of it is 1.4, and then times 10, because that's force of gravity, it's 14, sine 270, because it's going down, so then it comes out to sine 270, plus 2.8, because that's the radius all the way from here to the box, times 36, which is the force, because it's 3.6, and then sine 270. So after you do all this math, F here equals 54.73 newtons. And then here, for the system, you're doing the inertia system equals the inertia of the box plus the inertia of the plank. So you get 1/3 mbl squared plus mpl squared. And so when you plug in, you get 31.88 kilograms times meter squared for part B. And then for part C, you're using torque equals inertia times alpha, which is the acceleration. And so after you do all this, so then you have what torque is, which torque is RFB sine theta plus RFP sine theta. So then torque ends up equaling 120.4 newtons times meters. And then you already have the inertia of the system from part B, which is 31.88. So then right here, you divide the torque by the inertia to get alpha, and you get 3.78 radians per second squared. And then for part D, you're finding the real acceleration, so that's real A equals alpha times r, which is the acceleration times the radius. And so then you get 3.78 times 2.8, which ends up being A equals 10.6 meters per second squared. Okay, and then we move up to letter E. And so I got the third and fourth parts wrong. So tying the cord closer to the hinge would increase the tension because it'd be a smaller radius. So right here, this in the first equation, so the RF sine theta of the cord would be smaller. So you're dividing what you get here by a smaller number, so it would be greater. And then for moving the box close to the hinge, it would decrease because the radius for here would be smaller, so you'd be multiplying the 36 by a smaller number. So the radius of the box would be smaller, which would then decrease the tension.